Welcome to the course. Today we're going to talk about probably the most important algorithm, distributed algorithm. There's several very important ones. There's consensus, there's broadcast, what we saw before, and next week there's shared registers. If you want to make a distributed database, you have storage, okay? But today we will talk about maybe the most important one, and all the good ideas, distributed algorithms are in here. Consensus. I started last week on hierarchical consensus, which works with P. Regular, I'll go refresh your memory on that, and uniform. Then the point is, can we go weaker than P? I'll show you it works for S, the strong detector, which means that it's only making no mistakes with respect to one node instead of all. But the real question is, can we go eventual? Eventually P or eventually S? I will give you a theorem. It's impossible to make a consensus algorithm on a partially synchronous system that supports n over 2 failures or more. Now, this is called resilience. If you have at least n over 2 failures, it's impossible. So any algorithm will be less than n over 2. Then I'll show you the algorithm rotating consensus, which works for eventually S. And you'll see it's subtle, a subtle algorithm. And the trick on this algorithm is, when do you stop? But you'll see that it's a little bit tricky. So I'll show you, I'll explain that. And this one actually needs less than n over 3, which is a strange number, to make it work. And then there's even more better algorithms. There's the Paxos algorithm, which I will not explain, but we will go later in the course on other consensus, and if there's time, I go into terminating reliable broadcast. So let me refresh a little bit your memory. Oh, wonderful. There it goes. Just first of all, refresh your memory on what it means. So all nodes propose, and then they decide. Propose, decide. So you can only decide something that's been proposed. Correct nodes will not decide differently. They all decide the same, and they will decide, and once. I'm not sure why it's flickering. Okay, so they all propose once and basically decide once. Okay, that's the regular consensus. And here we have agreement, but we can also have uniform agreement. Okay, so let me go quickly. So this we saw last week. Let me go very quickly on the algorithm we saw last week. So basically the algorithm works in rounds. You have n nodes and n rounds. And in each round, one of the nodes is the boss. Okay, why is it flickering like that? Don't know. One of the nodes is the boss, and in each round, that node gets a chance to be the one that decides which is the value. And it works because there's at least one correct node. So we saw how that works. So you have to let each one be the chance to be the boss. And the reason is this has to work with failures. So any one of these nodes can fail at any time, and it has to work. But you know there will be at least one correct one, and at least one highest ranked correct one. So that one is going to be the one that really decides. Okay? So let me go on. So this one is not uniform. So we saw the code. I'm not going to go over the code again. Okay. I'll go explain a little bit intuition of why it's correct. The rounds will increase. A node decides in the round in which it's leader. So every node gets a chance to decide and to be the leader. And the first one that's correct will be the one whose decision gets taken by everybody, okay? And it works, it terminates because of completeness of P. P will detect when nodes crash, so then you can go to the next round. So this only works because of P, okay? Because P is complete, because P will detect crashes. That's what completeness means, huh? If you didn't have a failure detector, this would not work, okay? And they will agree. So agreement, you have to take one of the leaders, the highest one. There will be a highest correct one, and that's the one that will decide and will do best effort of V, and everybody after will decide it. So this works because there is one correct leader with highest rank, a minimum ID, okay? So how many failures can this algorithm tolerate and still work? What do you think? How many failures? Yeah?
N minus 1.
N minus 1. You need at least one, that's correct. You need at least one correct node, but all the others can fail. That doesn't matter if all the others fail, as long as there's one correct node, it will detect. It will work. So you can see that the consensus using P is very strong. Of course, using P is the easy way out, because usually you don't have P. Huh? But this algorithm works with perfect. Okay, N minus 1. Here is another notation I introduced for the same algorithm. And it's important because later today I will show you a more complicated algorithm, the rotating consensus, which is like this one, but going around forever. And to make it easy to understand, easier, I want to show you a code which is kind of similar to regular kind of imperative code. So this code here is the code that's run on every single node. The I runs this, okay? So all the nodes run the same code. The only difference is that there's an I which can be 1, 2, 3 up to n. Okay? So every node will do this for loop. If R goes from 1 to n, if R is equal to I, so this is the round when it's the leader, okay? So you can see this for loop is modeling the rounds. It's going from 1 to n. And if R is equal to I, then it's the round that I'm the boss. It starts with P1, P2, and so on. Then I will broadcast my value for all send. This for all send is a best effort broadcast, and I will decide, okay? And then I will do a special funny operation called collect. So here I'm sending to all of the processes. Every single process here will receive. So the collect is like a receive. Notice the correct collect is not inside the if. This collect will be done on every process. So in round 1, you will have run this on every single process, on round 2, and so on. So the collect is kind of the interesting operation here. It's like a receive, okay? But it's a little bit smarter than that. There's a Boolean. It's in an if. So you can either receive from a node, or you can detect failure of that node. So the collect kind of combines those two. Either it receives, and then the collect is true, and then x prime is the value it gets, or there's a failure, and then the collect returns false. So then it won't do anything, okay? So it's false if the failure detector detects the sending node as false, and also it's very smart, it drops orphan messages, okay? So this is actually a very compact way of writing exactly the same algorithm we saw. Okay? So it's important to understand this, because I'm going to use this notation in a few minutes to do more sophisticated algorithms, okay? So you can translate this to the event model we saw. It's very easy to translate this, but this notation is maybe easier to read because it looks more like a standard sequential language, okay? Notice, of course, there's a difference between R equal I, so this is done only for the leader, and the collect, which is done on all nodes. So this code runs on all nodes. All nodes run the same code. Okay, so you see, understand how it works? So this collect is an interesting operation. It's returning true or false. And of course, this is what triggers going to the next round. Because this is the last thing inside the for, and when this collect is done, it goes to the next iteration. So this collect is like what triggers you go into the next round. So you understand this notation? It's not so complicated, but you have to be a little bit, you have to think a little bit at first to get it. So this is the same algorithm we saw before, okay? But in a more compact notation. You see that? So now I want to do a little bit more. So we did regular consensus. Now I want to do uniform consensus. So this algorithm here is not uniform, and I'll show you an example why it's not uniform. And the reason is it decides too quickly. If you decide and then you fail, then the other nodes can decide differently. And in a uniform, then if you decide and you fail, the others have to decide the same thing. So here, you're deciding very fast, right after that you send the for all. So this is too fast. So the way to make it uniform is to delay the decision, okay? So let's make this thing uniform. So the same code now can be made uniform. And the idea is to move the decision to the very end, at the last, when you're at the end of round n. Okay? So all of these guys will now run all of the rounds and then decide. You're slowing down the decision a lot here. You're deciding at the end. But that makes it uniform. Okay? So what happens if a node decides here and then crashes? What happens with the decisions of the other nodes? Are they the same or are they different? What do you think in this case? So what happens if, like, node 3 decides and then crashes? It's deciding at the end of n rounds, yeah?
After deciding, the node wouldn't do anything, so it
Yeah.
takes the decision and the other nodes will do the same. And
Yeah, when you decide, you've already finished everything, and in fact, somewhere in the previous rounds, there must have been one correct node, so it already broadcast the same value. So that means this value is going to be the same for all the others. Because one of the previous ones will have broadcasted because it's correct. At least one of these previous ones has to be correct. So this is uniform, okay? This one is uniform. So we're good now. We have regular consensus and uniform consensus, but both of them use perfect failure detectors. You need the perfect failure detectors to go from one round to the next. That's why you need P. Of course, now what we want to see is what happens when we make this eventual. So that's the main theme of the course. We want to make internet algorithms that are very strong and that run on this very strange environment, which is the internet, which is partially synchronous, and where you don't have perfect failure detectors. So we want to weaken the failure detector. Okay, first of all, this algorithm that we just showed you, it works for strong detectors. Strong means that it only is perfect with respect to one node. That means if you have n nodes, one of them it will never make mistakes, but the others it might falsely think they crashed. But there's only one where it doesn't make a mistake. But that's okay, because we're making rounds going from 1 through n. So during these rounds, we will always, at some point, hit on the one node that is the one that we don't make mistakes. So S means that there's one node that we will never falsely suspect, at least one. Whereas P, we're never making mistakes with nobody, we're making mistakes. But since we're going through all rounds here, then we're going to hit on this one that makes it S. So this algorithm actually works for S, okay? But it doesn't work for inaccurate, okay? Let me get rid of this thing here. I thought this only happened with Windows machines. Seems to happen also with Macs, where you have weird messages appearing. Okay. So that also happens with Macs. It also happens with Macs. So here is an inaccurate. Let me see if I can get rid of this thing anyway. So here is the same algorithm, but now let's look at one of these eventual detectors. Okay. So eventual detectors start by making mistakes. That's how they start. And that means they're inaccurate. They start by falsely suspecting. So here is the same algorithm we saw before, the non-uniform version, going through 3 rounds. And you have these false suspicions. So all of these nodes are correct, but P2 suspects P1 and P3 suspects P2. Yeah, it's allowed. It's not perfect. Okay, so P2 thinks that P1 has crashed, but P3 will take the A. Okay, so P1 decides A. P2 now, P2 thinks that P1 has crashed, so it goes to round 2, and it decides B. So we're already wrong here, and P3 will suspect P2, but P3 does not suspect P1. So P3 will also decide A. Okay? So because of these 2 false suspicions, we have A, B, A. Clearly this is wrong. Okay? This is not working right. So these false suspicions will break our algorithm. Now this is the non-uniform version. We can do the same kind of experiment with the uniform version, which is the one that decides at the end. Okay? And we'll see it has the same kind of problems. So here we're going to run the uniform version. P2 suspects P1, P3 suspects P2, and P1 suspects P3. Okay? We're allowed to do that. Okay, so P2 suspects P1. Good, so this A does not arrive at P2. Okay. And here we continue now. P2 sends B. It doesn't get the A, so it thinks B. Okay. But now this B will arrive at P1. So P1 will actually decide B. But if you look at the round 3, okay, the P3 suspects, sorry, P1 suspects P3, so the A will not come into P1, but the A will arrive at P2. So you will have still different decisions, okay? Because it's different from the non-uniform version, but still the fact of deciding at the end doesn't fix things, okay? So in this case, we're unlucky. We have to invent another algorithm, okay? This algorithm does not work for eventuals. Okay, so the point is we want to go to a weaker failure detector than P. we're going to look at the strong detector now. Strong is a funny name because it's weaker than P. So what is the strong detector? It's strongly complete, just like P. So it will detect every failure, but it can make mistakes. But it's weakly accurate, but it makes a lot of mistakes, except there's one node that it will not make mistakes with. So it actually has a good view on one node, but not on others. So there exists a correct node which is never suspected by any other node. So one node, there's no mistakes with respect to this one node. But it can make mistakes with everything else. So it's kind of like P, but it's only accurate, so it's only not making mistakes with respect to one node. So it's weaker than P, yeah? P is stronger than this because P never makes mistakes. The S can make mistakes, huh? Except with respect to one node it cannot. But with respect to all the others it can make arbitrary mistakes, always, okay? It's not even eventual, okay? It can forever make mistakes to everybody except for one node. So it's a weaker detector than P, but it's called the strong detector, okay? So we keep that terminology. Okay? So our algorithm, I mentioned it actually, our algorithm actually works for S, huh? Because you're going through all rounds. The rounds increase monotonically. Okay? So this is the uniform version, only on the sides at the end. Every correct node makes it to the end. And the reasons are S is complete, just like P. So that means when a node crashes, S will detect crashes, and so it will advance to the end round, okay? So that's one thing. The other thing is, will they agree? Okay? Okay, because S has one special node that it's accurate, well, we're going to take this one, an accurate correct leader. Such a node exists. Okay, because that's what S means. This node, this one, S, special node, will do a best effort broadcast, and everybody else will get the message because they will not falsely suspect that node. Huh? So they will get the message, and afterwards everyone will have the same value. Okay? So basically it works for S. So the uniform version works for S, and the reason is that you're going systematically through all nodes, and so you will hit on that one that's the special one for S. Okay? Okay, great. So now we're making a little bit of progress. We have an algorithm that works for S. Yes? Question?
What if the special node suddenly crashes?
It cannot. There must be one that doesn't. That's S. That's what it means.
So
There must be a correct node that you do not, that is the definition of S. There must be at least one correct node that you don't make mistakes with respect to.
So
It's all in the S. So there's this one really special node actually, yeah? It's correct and you're not making mistakes. But you only need one like this. Whereas in P, all of them are no mistakes. Huh? But you have actually in S, you have actually one correct one. You have to have one correct one. There exists a correct node which is never falsely suspected. That's S. Okay. So that's in the S. Okay. You have actually one very special node. But we're still not eventual. Okay. So that's the whole subject for today. We want to go to eventual, and it's not so easy now, okay? Now we get to the case when making it eventual is actually hard. But we will get an algorithm, huh? But it's a little bit harder than the previous ones we saw. This is the first time in the course we actually have a subtle algorithm. We want to make consensus eventual, okay? That's the point. I'm going to show you a nice algorithm, but before that, I want to show you a limit. I want to show you a theorem. You cannot make it eventual where it has to survive at least n over 2 failures. Okay? I can prove that. We'll make a proof now, formal proof. An eventually perfect detector cannot solve consensus with resilience at least n over 2. So if there's at least n over 2 failures, so resilience means how many failures it can tolerate. Huh? So if you have at least half of the nodes failing, then you cannot make a consensus with an eventually perfect detector. So any consensus algorithm, the best one, will be for less than n over 2. Huh? And then the question is, how close can we get to n over 2? Can we get just underneath? Actually, we can get just underneath. But that's a very famous result. And there's a very famous algorithm called Paxos that lets you do just less than n over 2. But that algorithm is complicated, too complicated for giving in one course. Today I'm going to give you an algorithm that goes to n over 3. Later in the course we'll see an algorithm that goes just under n over 2. Okay, so let me show you now the proof. This is a very interesting way of reasoning. Okay? We're going to make a proof by contradiction. I'm going to assume that I have a consensus algorithm that works for n over 2. And then I'm going to show you a contradiction. I'm going to assume it's possible. And I'll show you a special case, but you can easily see it works for any number. I'm going to show you the case where you have 10 nodes, and we have an algorithm that works if you have 5 failures. Okay? And we assume that we have a consensus algorithm that works for 10 nodes and resists up to 5 failures. Okay? Okay, so how do we reason now? We're going to assume it uses eventually P. Notice eventually P in the beginning will let you do any amount of mistakes. Okay. So let me make some scenarios. So I'm going to show 2 executions of the algorithm, and I'm going to take pieces of those 2 executions, and I'm going to combine them, bricolage. I'm going to build another execution that's contradictory. Okay? So here I have green nodes and blue nodes. Assume now the green nodes are correct, and the blue nodes have red X's, so they crash. And assume the detectors are perfect. So that's allowed. An eventually perfect detector is allowed to make no mistakes. So assume that. All these guys propose 0. And these are crashed, and they are correctly detected by the green nodes. That's clear, huh? They will be correctly detected. So the result of this algorithm that it will decide 0, right? Assuming we have this algorithm, 5 nodes are crashed, and it correctly detects them. The other 5 will decide 0, right? That's reasonable. That's absolutely reasonable. Now let me show you another scenario, just opposite. Let me show a scenario where the blue nodes are now correct, the green nodes have crashed, and the detectors are all being perfect, no mistakes. And the blue nodes all propose 1, so our algorithm, we assume it exists, will decide 1 in this case, clearly. There's 5 correct nodes, they all propose 1, they detect this failure, they decide 1. Now, so you have these 2 executions. One of them decides 0, one of them decides 1. Now let's bring them together. And maybe you already are getting some idea of where we're going here. Okay, we're going to now assume that the detector is making mistakes. But we're going to assume it makes mistakes in a certain way. So we're going to assume that the green nodes will incorrectly assume the blue nodes have failed for enough time that the algorithm will give a result. So that means the green nodes will decide 0, like before, okay? And you can see where we're going now, because we're going to do a similar assumption for the blue nodes. We're going to assume that the blue nodes incorrectly think the green nodes have crashed for enough time, t1, that it allows the algorithm to decide here. So from the viewpoint of the blue nodes, it's exactly like before. Huh? They don't see any difference. So they will decide 1. Now this is kind of weird. Huh? We have 5 nodes deciding 0 and 5 nodes deciding 1. That's not really agreement. Huh? So there's a contradiction here. Huh? We have made a contradiction. So how does this actually, we can formalize this. Huh? Let me just give you an idea. So this is called partitioning argument, where you group the nodes into different partitions. Okay? So the way to formalize this, to make it completely rigorous, is to reason about executions. Okay? Sequences of events and configurations. Okay? So we don't worry about time. We look on prefixes. We take the schedule where you have green nodes running. You take the schedule where you have the blue nodes running, the first 2, and you combine the 2 schedules to make a third one, which is completely valid. As I showed you before, assuming that the failure detector makes certain mistakes, which we can assume, it's totally possible. So combining these 2 correct schedules will give you a third valid schedule where the nodes are deciding differently. That's not allowed according to agreement. That's a contradiction. See that? You see how the reasoning works? You get the reasoning here? It's a very simple reasoning. And you can see that n over 2 is kind of a breakpoint. There's a symmetry there. Okay. That's kind of annoying, right? It means there's a limit. But at least it's not totally impossible. It's only impossible for n over 2. Okay? So the question now, legitimate question, is it possible to do consensus at all with an eventually perfect failure detector? Is it even possible? We've shown that there's a limit. It has to be less than n over 2 failure tolerant. We will show it's possible. We'll show it's possible for eventually S. Okay? Of course, also the number of failures would be less than n over 2. I'm going to show you an algorithm that works for eventually S. So this is weaker than eventually P. So the algorithm that I show you on eventually S, will it also work for eventually P? Will it? Okay, eventually S is weaker than eventually P. Will the algorithm work for eventually P? What do you think?
Yes, because the restrictions are less.
So eventually S, okay, eventually S will do the following. It will make, for all nodes except for 1, it can always make mistakes. For 1 node, it will start by making mistakes and then stop making mistakes. And eventually P will, for all nodes, stop making mistakes. So what do you think? Will it work for eventually P? Oh. Really? Will it? Sure? Are you really sure? Wow, this is very difficult, it seems, huh? Let me let you think about that. Actually, it should not be so difficult, right? Eventually S, so eventually P Will it also work for eventually P? So I have now an algorithm that stops making mistakes for all nodes. So clearly, it will stop making mistakes for one node. Huh? Okay, look. Let me let you think about that. Okay, I'm going to show you an algorithm now that works for eventually S. And then we'll talk about eventually P. Let me recall to you what eventually S means. Okay, eventually strong. It's strongly complete. Eventually every failure is a detector. That's the same as eventually. It will detect every failure after some time. But this is different. The accuracy is different. It's eventual weak accuracy. So eventually there's a correct node which is never suspected. That means it starts by making mistakes with respect to everybody, but after some time there's one node that doesn't make mistakes for anymore. But it can still make mistakes for the others. Okay? So accuracy with respect to one node, eventually. So there's a special node, and that one, everything is built on top of that one node. Huh? Okay? So you see how it works, huh? There's one special node that will stop making mistakes. But everybody else, it can keep making mistakes, huh? Forever. That's a pain, huh? But luckily, there's this one special node, and that's enough. We can build our whole algorithm on top of that one special node. Of course, we don't know which one it is, and we don't know when the mistakes stop. So that's the whole trick, yeah? How can we make an algorithm where we don't even know when it stops making mistakes? That is why it's subtle. Okay. So I'm going to go through this step by step. First of all, the original algorithm, the one which I call hierarchical consensus, this algorithm will clearly not work. Huh? And it's very easy to see. Eventually, it stops making mistakes. But eventually might be after n rounds, of course. Huh? This one only does n rounds and then it stops. Okay? But eventually might be after that. So during the n rounds it might be making mistakes all the time. So clearly that one doesn't work. Okay, that's clear, right? So what's the trick now? What's the trick? It's actually, it starts by being very easy. You go n rounds, but the eventually might be after. So what do? Well, you keep circulating. That's the trick. That's the first trick. So the basic first idea, it's called a rotating coordinator. So you go around 1 to n, and then after round n, you start again round 1 to n, and then 1 to n. So you keep going round and round and round forever. You never stop. Okay? And that will, at some point during that circulation, the one node, you won't be making mistakes anymore. Okay? Eventually, all nodes will be correct with respect to one coordinator. Okay? At some point in the future, there will be one coordinator and nobody will falsely suspect it. That means they will all receive messages from it. You see that? They will not think it's failed, so they will all receive the value it proposes, and from that point onwards, they will all have the same value. You see that? Of course, you don't know when that's going to happen, huh? So you see the point, huh? At that point, somewhere in the future, where we don't know when, but somewhere in the future, this one node, everyone will see it and not think it's crashed, and they will get its value, and from that point onward, they will all have the same value. And that's great. But the problem is we don't know when it's going to happen, okay? You see? So this is the idea, but the trick is, how do we stop the algorithm? That's the real issue, huh? Okay? So of course, like there's a problem here, huh? So you see how it works, right? You're getting it, huh? That there is some point in the future where they will all have the same value. You see that, huh? You don't know when, but that point is there. It exists, huh? You see it, huh? Everybody sees it, right? And everybody sees that there's a problem, okay? The problem is, how do we know when? When does it happen? That is the whole trick of this algorithm, okay? The whole trick is to know when to stop. And that's why this algorithm is subtle. It's not that easy to know how to stop. How can you somehow know how to stop? Isn't that kind of amazing? It's possible, huh? We can make an algorithm that at some point it knows that there's no more mistakes, and it stops. Magic, okay? Okay, let me just say a few words. So I'm going to be explaining this subtlety. It's going to take a while. It's actually very simple, but I want to go really step by step so you can see what's really going on, huh? But we have to start, you get it, right? Because if you don't understand this, you will not understand any of the rest, huh? If there's any doubt on this, you have to yell now, huh? You get it, huh? You rotate forever. Eventually, you will hit one coordinator with no mistakes, and then you will have all the same value. You see that, huh? And the point is, you don't know when it happens. You see that, huh? That's simple, right? It's not complicated, actually. Right? Okay, so I'm assuming everybody knows that. Okay, so how does it work? Okay, we can make it work if the number of failures is low enough. Actually, this one, we can make it work if the number of failures is less than n over 3. That's weird, huh? Why n over 3 and not n over 62 or something, huh? Well, you'll see why. So if the number of failures is less than n over 3, we can actually make this work if there's not too many failures, okay? Less than a third can fail. And then we can use some kind of majority, but we'll see how it works, huh? So here's the actual algorithm, huh? I want to be very specific about it, and I'll show you the code, huh? So this loops in rounds. And in every round you have this. Everybody sends their vote to the coordinator, okay? The coordinator receives from all the nodes, it picks the majority, and it broadcasts that majority. Every node will receive what's been broadcast and changes its vote. So we'll make a picture now of this, what happens during one round, because that's super important that you get it, okay? So this is one round. Assume that this guy is the coordinator, so the coordinators will change, huh? Everybody will send their vote to the coordinator. Vote, vote. The coordinator picks the majority, and it will then broadcast the majority back to the others. So this value that's broadcast will be the same for all of them, huh? Some value v, whereas here they might be different values, huh? So this is what happens during one round, huh? Round C, and then we have C plus 1, etc. Now this looks very straightforward, huh? And if PC is correct, then it's done after this, clearly, huh? If PC is allowed to do a best effort everywhere, then they will all receive the same thing. Now, of course, the problem is that we have eventually S, and the problem is also that some of these nodes might fail, okay? So when everything's correct, this is easy, huh? But of course, we can have make mistakes with respect to failures, and nodes can actually crash too. Less than n over 3, but they can crash. Yeah?
How do we decide which node is coordinator?
How do you decide? Well, it's like the first one. You start with node 1, and then you go up, you go up forwards. Okay? So you have also a completeness. So the nodes can actually switch to the next round. So you are also cycling through the coordinators from 1 to n and then from 1 to n. So you're going through it like that. Huh? So at this point it's C, but then the next round it'll be C plus 1 and so on. Huh? Okay? So everybody sends the vote to the coordinator. C receives votes, picks a majority, broadcasts it. Every node will receive that broadcast, maybe up, maybe not, because maybe the node thinks that C has failed, but if it doesn't, it gets the broadcast. It changes the local value to V, and then you go to the next round and you repeat. And this goes on forever. So this is the rotating coordinator. It goes on forever until, by some magic, we figure out how to stop. Okay? So that is the idea of how the algorithm works. And the trick is to find some condition here that lets us stop. To figure out at some point that we're allowed to decide that all the values will be the same, and so we can stop. Okay, so that's the trick. How do we figure out when to stop? Okay, so let me now make a break. After the break, we will go into the details. I will show you code after the break. And we'll go through the actual execution. But you see the idea, huh? It's important to see that, huh? Okay, so now let's make a break. After the break, we dive into it. We'll start by showing you the actual code of the algorithm. So everything is very clear. You see the idea, huh? That it's rotating forever. This code is using the similar notation as before. So the same code is running on all nodes. And you can see, instead of a for loop, you can see there's a while loop here. Huh? That's clear. Huh? We're running forever. While loop. And there's an incrementing of the round number. But this increment goes up forever. Huh? But the actual coordinator is r mod n plus 1. So you see this guy is going from 1 to n and then from 1 to n. It's very clear, huh? And this code is running on all nodes. So I'm now sending my value to the coordinator, which is PC. So all nodes will send to the coordinator. Huh? That's the first piece. So there's 3 pieces. Huh? The second piece, there's an if statement now. If I is equal to C. So this code is only running on the coordinator. Okay? Okay, it's the same instructions on all machines because all nodes will eventually be coordinators. So the code has to be there, but it's only running if I is equal to C. Okay? So PI, this code is copied n times. Huh? For P1 to Pn, where the I is the number of the process. Huh? So I is a constant here. Huh? It's not a variable. Huh? You see it. Huh? I'm being very, very clear now, huh? So that you can really understand it. Huh? So this is like parameter constant. And this code has n copies with n different values of I. Okay? Whereas C is a variable, of course. Huh? And I'm incrementing each time. Okay? So if I is equal to C, this code is running only on the coordinator. Huh? It's this piece. Huh? Okay? Very clear. Huh? Now, this is a simplified, slightly simplified consensus. I'm only going to propose 0 and 1. You can make it more complicated, but it doesn't change anything. So I don't want to make it, I want to make it as simple as possible. So there's only 1, and 0 and 1 are the only possible proposed values. So now I'm going to receive messages, okay, from other nodes. Now the trick is, notice that I'm sending n messages here, huh? But I'm not receiving n. I'm only waiting for n minus f. Okay, that's important. It works. I'm not going to wait for all of the n. In fact, they might not even all arrive, huh? Because some of these nodes might have crashed. I can have up to f crashes. So in fact, I will only receive in the worst case, I will only receive n minus f. I might receive more, huh? But I only have to wait for n minus f messages. Okay, that's very important. And I receive a message, and I'm receiving them, and I'm counting how many zeros and how many ones. So the v here can be 0 or 1, and messages v. So this is like kind of a mixture, a C-like notation, pseudocode. So I'm incrementing either the 0 array, the 0 value, or the 1 value. So messages is a vector with two things. So I'm counting how many zeros and counting how many ones. Okay, see it, huh? So I listened for n minus f messages. I count the zeros and the ones. If the number of zeros is greater than the number of ones, then the coordinator will decide on 0. It's going to pick the majority here, huh? Otherwise, it will pick 1. If they're equal, it doesn't really matter. Okay, we'll see. So if one of the zeros are greater than the ones, it picks 0. And then it will send that majority to everybody. For all j, this is from 1 to n. Okay. Send v to all. So you see, it's doing exactly like this, huh? But it's only receiving n minus f messages, but it's actually sending n. N minus f because in the worst case, it will only get n minus f if we have f failures. It might get more, huh? You don't care. It's enough to get n minus f. We'll see. Okay? So you see how it works, huh? It's clear? This code? It's totally clear. This code, it should be very precise, huh? And then the third part is executed on each node. So that's these pieces, huh? The ones executed on each node. I'm using this collect. Okay, so I either get a value or I get a failure. The coordinator might fail, huh? And if I get a value, then I just assign it locally. So I adopt it. So the v values will be made local. That's it. Okay, that's the code. There's a small thing missing here, huh? So this code will run forever, huh? I'm going to add one small thing to this code to make it stop. But right now, this code will not stop. It'll just keep running forever. You see, huh? Okay. Now I want to show how to make this code stop. Okay. In order to do that, I want to first talk about the f and the n minus f. Okay. So I want to do something which I call the majority lemma. So basically, I want to think about the f and what is the role of that. The f and the n minus f messages. Because of that f, we can actually do something. So here is the majority lemma. We can prove this. So this is where the f less than n minus 3 comes in. Okay, it comes in here. If at least n minus f nodes vote v in a round, then in all the rounds after that, everybody will see a majority of v. There will always be a majority of v. Okay? So that means at some point, if we have this, then if the n minus f somehow installs itself, okay? If n minus f somehow managed to vote v, it will be forever v, okay? We can prove it. So let me make first a diagram to show you what it means in the execution. So here we have rounds, huh? We have many rounds, and it goes on for a long time. So assume here we have n minus f vote v. Well, if that happens here, in all the rounds later, majority will always be v. That means all the coordinators will always see v after that. Okay? Now, it's not telling us whether this happens, but if this happens, it gets fixed. And I can prove that. I'll try to explain it in a couple of different ways, but it basically based on two things. One is that there's less than n over 3 failures, and two is that I'm waiting for n minus f messages. The coordinators wait for n minus f messages, and they're looking for majority in that. So from these two, we can prove something. Okay? So here is kind of the reasoning. So all nodes vote. The coordinator waits for n minus f messages. Okay, here's coordinator. It's getting n minus f. And all nodes vote. Okay? Okay? Now, we know this. At least n minus f nodes vote v. But how many of those n minus f will reach the coordinator? Maybe not all, huh? They might vote v and then crash right after that, huh? So but you have you have f failures. So the coordinator will maybe not get all of those n minus f, but it will get some of them. The coordinator will get at least n minus f minus f. The f failed nodes it will not get. Okay, it might get more than this, huh? If there's less failures. But if you have f failures, then the coordinator will get this. Okay? N minus f will vote v, but f failed. Okay? And since the coordinator is waiting for n minus f, then it will also get f values that are different from v, because the sum of those two has to be n minus f. Okay? So there's n minus f, which are equal to v, and there's f, which are different from v. Okay? That's very clear, huh? So what can we say now? It turns out that f is always less than n minus f minus f. That's weird. How come? Well, it's because f is less than a third. If f is less than a third of n, okay, then n minus f will be greater than 2/3, and n minus f will be greater than a third. And f is less than a third, okay? Since f is less than n over 3, this implies that f is less than n minus f minus f. You can calculate this. And what does this mean? Well, we can actually simplify, yeah? F is less than n minus 2f, 3f is less than n. What do you know? It's exactly the same formula, in fact. This and this is actually the same formula, just written in a different way. You see that? So because f is small enough, so the intuition is, because f is small enough, n minus f will be big enough to be the majority. So the majority is n minus f. So the majority is part of these n minus f voting v. Okay? That means the coordinator will pick v, because it picks the majority, and it will, oops, well, there you go. So then the coordinator will send v to everybody, okay? And in the future, the coordinator will send v's. So some of those v's might arrive, huh? some of those V's, the coordinator will now send V's to all the others. So what that means is that in the future, the number of V's can only increase. The number of V's can only increase since the coordinator is now sending more V's. That means every leader will now see a majority. So that means if you have at least n minus f voting V, you will always have the majority, so n minus f voting V, always. So it kind of installs itself forever, okay? So it kind of gets fixed in the system, huh? Once you have n minus f V's, it kind of gets fixed in the system, huh? It never goes away anymore. You see that? And the reason is, why is that? Because it's the majority. And why is it the majority? Because f is small enough. So the trick is, f has to be small enough. It turns out we can make it up to n over 3. And the reason why n over 3 is because there's 3 f's. There's an f, and there's another f. So we can make it up to n over 3. So somehow there's this 3 that appears because of the 3 f's. So the n minus f, where you have to subtract f because of the failures, and on the other side you might have f that are different. Okay. So this is the key thing. Okay. This is something you have to understand. The intuition, so on one side there's intuition. If f is small enough, then a majority of n minus f will be big enough that even if you have failures, it will not go away. That's the intuition, huh? And then the point is to calculate exactly the value, the threshold, the exact value of f that is that makes the difference. Huh? It turns out if f is less than n over 3, then this holds. Okay? So this is the key reasoning to make this whole thing work. Okay? Now the rest now is pretty easy. Basically, the rest is showing that this at least n minus f vote V, that it will happen. It will happen, and then showing how you can actually detect it. But the real point is this. Okay? This is the reasoning. Once you have n minus f majority, it will be frozen in the system forever. Okay? So that's the key reasoning. And now we can see what happens in the algorithm now with this. Okay? Okay? Okay, so what does the algorithm do now? So let's go back to the algorithm. So you can see the coordinator is waiting for n minus f here. Huh? It's waiting, and some of them vote 0, some of them vote 1. Coordinator picks a majority, continues. This continues. Okay? Now we can actually say something. These n minus f, some of them will vote 0, some of them will vote 1. Now if all of them vote the same, if they're all 0s or all 1s, then we can actually terminate. Because then we know that nothing can change the result. The decision that all the leaders will see that majorities, that they all vote 0. So the point is you're getting n minus f here, and some are 0s and some are 1s. But maybe they're all the same. Maybe they're all 0s and all 1s. If that happens, we can stop. Okay? We can stop because we can decide then. If it happens, we can terminate. And I'll show you, it's actually easy to show. It will happen because of that lemma. Okay? So if the coordinator sees that all the n of f are voting the same, then that's the decision. And the algorithm can terminate. Okay? So that is it. But there's still, of course, one small thing. How do we know that we get to there? Okay, that's the last point. Okay? But let me show you first the algorithm now, the code, and then I'll show you that this actually happens. And then we're done. And it's based on that lemma. Okay? So here's the code that we saw before. So this is the same code. So the gray is the code we saw before. So the while loop, the counting of the rounds, if I equals C, so the code inside and the code outside. Okay? Okay. In fact, so you're counting the zeros and the ones here. If the number of zeros is equal to 0, or the number of ones is equal to 0, that means that the n minus f messages are all the same. Then we can decide. So we add this Boolean variable, d, for decision. And if all n minus f are the same, I will make d equal to 1, otherwise d equals 0. And when I send the value, I will also send the d. So the coordinator will decide, okay, it will send the d, and the collect will receive the d, okay. So here, if there is a d, okay, I'm not sure why it's doing I. Because to only do it once. To only decide once. Yeah, so there's a rule. So if there's a d, if the d is true, then I decide. I is the number of the node. There's a funny trick. I set the number of the node to 0, so I only decide once. Okay, that's kind of a hack. It's actually, there should be another boolean. You see what it's doing, It's only deciding once. Because after that, it will set I equal to 0. I is supposed to be a constant, So that's a hack. So how do we know it's going to happen? Now we can actually use this eventually S thing. Now we're going to think about the eventually S. Okay? Okay. And now the algorithm is running. It's rotating round and round and round, and eventually that some node Q will not be falsely detected. No mistake. So we're at that point. We've arrived at the point where this node that everyone sees correctly is coordinator. Ta-da! We're arriving there. Might be very long, but we get there in this blue line. Okay? So everybody sees the coordinator and does not think the coordinator crashes. And coordinator picks the majority. Everyone collects, and the coordinator Q sends it to everybody, and everybody receives it because the coordinator is correct, and everybody now adopts V. So at the first time you hit this special guy, everyone will adopt V. Okay? From now on, all alive nodes will vote V. Okay? And the majority lemma holds, Now, but we're still running. We're still not done yet. Okay? But the next time around, when Q is coordinator again, so you have to go all the way around. Why do you have to go all the way around? Well, maybe you don't. Maybe it happens in the middle. But you're never sure, because you can always have mistakes. The nice thing about Q is you're sure there's no mistakes. So for sure, when you hit Q again, you will only receive the same value. Only all zeros or only all ones in the n minus f's, and then you're done. So you see how it works? And then you can decide. So we got there. Oof, I can see you are overjoyed to understand how it works, just like me. But you see how it's working? So basically, this thing, so the f less than n over 3 means that once you have a 0 or 1 frozen, it stays there, and it will not change. That's important. And then the next thing is the eventually S, but you have to hit the guy twice, because the first time you hit it, you might not have the same number. You might have some zeros and some ones coming in the n minus f messages, okay? But it's the next time around that you will have only zeros or only ones, and so that the messages will only have one value, and then you can stop. And then you're done. Oof. It's kind of subtle, no? Isn't it? What do you think? You see how step by, maybe you can follow what I recommend is that you look at the different steps. Actually, the slides here are better than the slides on the Moodle because I improved them this afternoon, yeah?
Did you update it like a Moodle?
Yes, I will put these slides on the Moodle because these have a better explanation. So I try to make the explanation better, and so I will put these slides in the Moodle. I think this is a better explanation than the one on the Moodle, huh? So everything is connected, huh? The f n over 3, receiving n minus f messages, maximum f failures, the rounds going forever, the eventually s, eventually no mistakes, but it's not enough you hit it once. You have to hit it the second time you hit it, you will actually be sure you're done. Not the first time, you won't be sure yet. And this is all worst case, huh? I mean, this is like the worst case. Maybe you can stop before that. If some other node has no mistakes. But there's no guarantee of that. There's only a guarantee for this one, okay? So this is really a worst case, okay? You can have much better executions than this, but in the worst case, this is what will happen. So it will still terminate in the worst case. Okay? Okay? All alive nodes will vote the same. Okay? And then when you detect that, you're done. So why do you have the majority lemma? You can summarize it another way. You could have n minus f voting 0 and f voting 1, and then you receive n minus f zeros and f ones, but you don't want that to give a 1, okay? So even if you have a majority of zeros, you still want the ones to go away, because if the f is too big here, if it's like n over 2, then the ones could still take over. So, but if the f is less than n over 3, then this guy, the zeros, will still be majority. Okay? Just a little intuition. Okay? Okay? Okay, this is I explained before, so I'm not going to repeat that. Let me summarize now what we saw on consensus. So we saw it first using synchrony. So synchrony means perfect. S or P. It's using S, but also works for P. It's partial synchrony, using eventually S with less than n over 3 failures. It turns out you can do eventually P with n over 2, okay, failures. So this is an algorithm called Paxos, which I'm not going to explain in this course because it would take several lectures, and I don't think it's useful actually. I mean, my analogy is that a long time ago, the ancient Greeks, Archimedes, famous Greek mathematician, determined the value of pi using geometry, okay? But people don't teach that anymore because using integrals is much easier, okay? So I'm not going to actually teach Paxos, even though it's a brilliant invention when it was invented by Leslie Lamport, but I'm going to show you a simpler version called Raft, which is just as powerful as Paxos and much more intuitive. Okay, so later on we'll see Raft. So most modern systems today are actually using Raft. Okay, Raft was invented around 2014, so it's not that old. And Paxos was like 1990, so it's much older, okay? So we'll see Raft later in the course. So consensus works for synchronous systems, n-1 failures, for partially synchronous systems, less than n/2 failures, and it doesn't work in asynchronous systems, which we saw already in the first lecture. Huh? If at least one process can fail, and you're in an asynchronous system, you can prove that you cannot, in general, solve consensus. This is like the generals, the Byzantine generals we saw, okay? So this is an interesting proof, actually, because you're proving, you're finding an execution which will never terminate, actually, yeah? So this is very mathematical proof, but it would take a whole lecture to show it to you. So I decided kind of heavy heart not to show it in this course, because there's so many other things to present. But the intuition is, if you have the model as asynchronous, you can get the intuition from the generals, huh? You have a messenger going from one general to the other, but you have to acknowledge the messenger. You have to acknowledge the acknowledged messenger, and you have to acknowledge the acknowledge, and so you can always find an execution that never stops. So that's kind of the intuition. And if you formalize that, you can show there's no general way of doing it, okay, in an asynchronous model. Okay, so that's it for consensus for today. And so later on we'll see Raft near the end of the course. And probably in your career you will see Raft or some later version than Raft. Okay, so now I want to show you something different from consensus, but it's related, called terminating reliable broadcast. And this is there's a very interesting intuition here, okay? So now, go back, remember now, in a reliable broadcast, let's say you have a chat application, okay? You broadcast a message, and the clients receive the message. But actually, the clients don't know when that message will be delivered, okay? They don't know when the message will be delivered. But how long should the clients wait? So, can the clients know when the broadcast is finished? Okay, so the regular reliable broadcast, the God's eye view, when you see the time-space diagram, you can see when the algorithm is done. But the individual nodes, they don't know when it's done. So that's a profound thing. How do you make the individual nodes know that the algorithm is done? That actually is not easy, okay? And it's actually related to consensus also. It's actually a hard problem, like consensus. How can a node know when the broadcast is done? This is called the terminating reliable broadcast. So it seems very small difference, huh? Because it's still doing reliable broadcast, only the difference is now each client knows when the broadcast is finished. Whereas in the previous one, they didn't know. That's the only difference. Okay? So, TRB is a reliable broadcast. The sender will broadcast. The receivers wait the delivery. And the receivers will either get M, they will deliver M, or they will know that it's done. They will abort. But abort is like a special message. They will either get M, here you go, the message M, or they will get a special message, sender faulty, whatever, SF message, saying that, sorry, you didn't get M, but the algorithm is done. Because remember, in a reliable broadcast, it's all or none, huh? If you get M, of course you know it's done, huh? You get M, the algorithm is done. But if you don't get anything, you don't know that the algorithm is done. But in TRB, you will always get something. Either you get M, or you get some kind of token telling you, sorry, you didn't get M, but the algorithm is done, and you won't get M. So this is the special message. So you will always get something telling you that the algorithm is done. Okay? So that's a terminating reliable broadcast. So this one is takes a lot more work than the regular reliable broadcast, actually. It's like telling you with a message when something did not happen is very hard. It's kind of like a negative information. Huh? In the distributed system, it's especially hard. So here is a terminating reliable broadcast. And in order to work, it needs a perfect failure detector, this one. So that already should make kind of alarm bells go in your head. Huh? An algorithm that needs a perfect failure detector, that means it's going to be hard to implement. And if you want a strong result, sometimes you need perfect failure detectors. Okay? So you do a TRB broadcast. Okay? So here all the nodes have to call it. It's a little bit different, huh? But the ones that don't broadcast will just send nil. They will send a nil message. So somehow all the nodes have to say the algorithm has started, and then all the nodes will see when the algorithm is done. That's how it works. Okay? They will get a TRB delivered, and the message either will be M, or it might be this funny SF message if the sending source node crashes. Okay? So this is very similar to reliable broadcast, but the difference is interesting to see the difference. Okay? So we'll go through it. So every correct node delivers one message, fine. If a correct source node sends M, it will deliver M. If any node delivers M, every correct node delivers M. Okay? But then here we have, if a node delivers M, then either M is SF or M was broadcast by the source node. Okay? So this is a little bit different from the regular broadcast algorithm. Okay? Let me see. Let me just make one more thing, and then I'll finish for today. So there's actually a connection with consensus here. Okay? So why am I talking to you about TRB? Because TRB is a hard thing, but the hardness is similar to consensus hardness. Okay? So let me explain. So the source node will do an RB broadcast, but if the source node is suspected, I deliver SF. Okay? So the idea is that if the source node does a BEB broadcast, the nodes will propose. See, you want all nodes to receive something. And consensus has that. It has decision by all nodes. So we're going to use consensus. So all nodes will propose either SF or M. And you will deliver the decision of the consensus. And in that way, all nodes will for sure get a message. Okay. Okay. This is, let me see. Okay. That's all I want. Let me stop here today. I just wanted to connect TRB to consensus. So the point is that consensus is like a building block, and you can use it to add strength to many different algorithms. So here we are using consensus to make reliable broadcast stronger by letting it tell you when it's done. That's actually making it a lot stronger, but that strength comes from consensus, okay? So you can see that consensus, especially the eventual versions, even the hierarchical one is somewhat complex, but the eventual versions are quite complicated, but that complexity gives you a lot of power. So consensus is actually a really good building block, okay? So here in TRB, consensus can tell you when the broadcast is done, okay, when it's finished. I want to say more here, but we don't have enough time today, and I don't want to rush things. So I will get back to this in the next week to give you more of the intuition. But what I want you to keep from today's lesson is, first of all, consensus, you can do it in eventual. You saw it, but you saw that it's not so simple, but actually, you can actually make it work in this really funny, eventually accurate, partially synchronous system. That's not obvious, When Leslie Lamport invented Paxos, it was like a revolution. Nobody understood that you could do that. Then he comes with this algorithm that kind of solves the problem, okay? So you can actually do it. And this opened up a lot of things, okay? So the work of Leslie Lamport in around 1990 and the work that came after, also failure detectors, that is what made clouds and data centers and big internet applications. It's what made it possible, okay? People don't usually say it so simply, Oh, social networks, clouds, wow, wonderful, Amazon, Google, those guys are geniuses. But they are building on this, okay? What Google does could not work if they would not have consensus, or Amazon either. You could not work with these very large, consistent systems. Amazon selling millions of things to millions of clients. It would not work without consensus, okay? So let me just finish today by just a little bit of philosophy that consensus is, in some sense, what made today's distributed systems possible, okay? And it's not simple. And it took serious work to come up with the consensus algorithms that work on the internet. But it was a major advance, and that's what make all the things that people take for granted today, these huge internet systems, Facebook, which some people think is very evil. I think it's also evil, but consensus is what makes this possible, okay? It could be non-evil, There could be a non-evil version of Facebook. Let's assume that we have a non-evil version of Facebook built on top of consensus. But all these internet systems, these large systems, are built on top of this, okay? And people don't realize that because it's underneath the hood. It's underneath. It's like traveling is built on top of internal combustion engines. People realize it somehow, Without these internal combustion engines, you wouldn't be moving around so much as you do today, A lot less. So consensus is a similar thing, Without consensus, you wouldn't be doing so many internet things today. You would be doing a lot less, okay? So this is just one example, TRB, of consensus as a building block. And maybe we'll see more examples. But in big internet applications, they're all built on top of this, okay? Okay, so that's just a little bit of philosophy, but let me stop today now.